good way to think about what I'm going to do in the rest of the lecture is just explain how to make co-compact lattices in SO1N. That's a good way to think about what I'm going to do. There's going to be sidetracks and some other important ideas, but that's the thing. If you want to construct co-compact lattices, you pretty much have to know what I say in the rest of this lecture. So let me just give you an example. Okay, so let's let alpha be the square root of 2, just so I have a simple name for it. And then I'm going to define a quadratic form, and it's the one we usually have. It's just the first one's positive, the rest are negative, so it's of type 1n, except I put an alpha in front of all the negative coefficients. Okay, so all the negative terms have an alpha on them instead of just being a 1 on them. And then I let G be the orthogonal group of this form. Well, there's one positive sign and all the rest are negative, so this is a type 1n form, so I've got SO1n here. And then I let gamma, as always, be the integer points of G, except there's a little bit of a problem here. It turns out, since I've stuck this square root of 2 in, I want to look not just at ordinary integers, but algebraic integers. So I need to take the z adjoint square root of 2 points. The z adjoint square root of 2 points of G, not just the ordinary integer points of G. So up till now I've always just taken G sub z, but in this example I want to make my ring bigger because my group is more complicated. I've got the alpha in it. And so of course what I mean by that is just take G, but look at the matrices in there whose entries are all integers with square root 2's. That's my group. And the point is, the main thing I have to explain in the next 45 minutes, or 40 minutes, is that, in fact, gamma is an arithmetic subgroup of G, and not just any arithmetic subgroup. The trouble is, even that's not obvious. If I was using z's everywhere, then it'd be arithmetic. It's not obvious, but it turned out this is an arithmetic subgroup, but that's not so interesting. What's really interesting is, in fact, it's a co-compact arithmetic subgroup. And this is for any n. So I said we had to do something more sophisticated, and the more sophisticated thing we have to do is just use rings of integers instead of just ordinary integers. That's what we have to do. But let me explain why this is a co-compact arithmetic subgroup. I think it's not obvious from what I've said so far. And first thing, though, is let me say that I'm going to talk about the fact that it's arithmetic subgroup later. Okay, let me worry about that later. Right now I want to, let's assume it's an arithmetic subgroup and just see that it's co-compact. Okay, that the manifold is compact. And the key point is that we've got these criteria for compactness. I can look for G's and gammas, or I can look for unipotent matrices, or I'll do the one that I told you today is easier. I'm going to show that there are no anisotropic vectors. That's what we want to show, is that there's no anisotropic vectors. That's the criterion, except just like up here I had to use integers with alphas, it's the same thing down here. Once we've shifted from z's to z adjoint alphas, Q is no longer enough. Our entire field has changed. I mean, Q is not the field anymore, it's Q adjoint alpha. So, but I think you can probably believe that this is the right condition for that group. If that's an arithmetic group, then our integers have changed to algebraic integers. Our field Q has changed to an algebraic number field Q of alpha. All right, it's purely analogous to what we had before. That's the thing here. So I want to prove that Q has no anisotropic Q alpha vectors, and then I hope at least you'll believe it's reasonable to think that this is a co-compact lattice. Right, so let's talk about that now. Right, so this is the setup. I've got Q as this form with some alphas on it. I want to show that Q has no isotropic vectors. And the proof is, well, just let's suppose there is an isotropic vector. So suppose Q of some V is 0. Well, I need to look at this is an extension field of Q, so there's a Galois automorphism of this extension over Q, and it just sends, I'll call it sigma. Elements of Q adjoint alpha are rationals plus a rational times alpha. The automorphism just sends the square root of 2. Yeah, remember alpha just means square root of 2. It just sends the square root of 2 to minus the square root of 2. So that's the field automorphism of this field. It's the Galois automorphism of this field. And if I apply that to the quadratic form, here's my quadratic form. If I apply sigma to the quadratic form, it's just going to, well, there's nothing to happen here, but all these alphas will turn it into minus alphas, but they were being subtracted, so the quadratical form will have all plus signs now. That's the thing. If I apply this automorphism just to the coefficients of that polynomial, I get a new polynomial, which I'm calling Q sigma, and it's got all plus signs. So the key thing is that, well, we'll see this later, but this now is a quadratic form with all plus signs. It's obviously got no isotropic vectors. SO of Q sigma is SO n plus 1. It's a compact group. Right, but anyhow, so let's suppose, I'm supposing Q of V is 0. Well, If Q of B is 0, when you apply a field automorphism to it, it'll still be 0. And now let's calculate this. We know what Q of B is. Oh, I didn't write it down. This is Q of X. Q of B is the same thing with all B's in it. And now if I apply a sigma to that, okay, well, I'll get V0 to the sigma squared. A sigma, I mean, because sigma is a field automorph, so you can apply it to everything independently. That's what I've done. Whoops. Yeah, okay, I did right. Yeah, so I'll get minus sigma of alpha, but sigma of alpha is minus alpha, so they'll change that minus sign to a plus sign. So all the minus signs change to plus signs when you apply sigma to the alphas, and then I just applied sigma to all the b's. Okay, so that's, I've just applied sigma to each term here, but with b instead of x. This is what I get. And you notice that that is, what is it? Well, if you take x squared plus alpha x squared plus alpha x squared, that's exactly this q sigma thing. So I'm taking q sigma of v sigma. Right? This is just that quadratic form, but with the vi sigmas in place of x. But this quadratic form, remember, this thing has all plus signs, right? All the coefficients here are positive, so there's no way to stick a vector in and get 0 unless that vector is completely 0. So v sigma must be 0. There's no way to make that form 0. It has no isotropic vectors even over R, but if a field automorphism sends something to 0, that something must be 0. That's what it's trying to prove. So even though this thing has both plus signs and minus signs in it, there's no rational isotropic vectors, or even if you apply add the square root of 2 to it. And that's, from that we see that G mod, that X mod gamma is compact. Right, so let me say, so this, if you understand what I've done here, there's a more general thing we can do. The same argument works more generally if you have not just a single alpha, but have a whole bunch of alphas that are algebraic integers, maybe square root of 2, square root of 3, cube root of 7. There's a whole bunch of algebraic integers. And the first one is positive, but the rest are negative. So last time what I had was I had 1 for my alpha 0, and negative square root of 2 for all the rest of them. If you make, so we can have a quadratic form, we'll look at alpha 0 times x0 squared plus alpha 1 x1 squared plus alpha 2 x squared. That's what I'm going to do. These are the coefficients of my x's. And the crucial thing, though, is that we started out with one guy positive and all the rest negative. That can be type 1n. When I applied the Galois automorphism, everybody turned positive. Right? Well, it turns out that's exactly what it means. So let's assume that for every Galois automorphism of the field, so all the automorphisms of the field containing all of these alphas, when you apply that to each alpha, either everybody is positive or everybody's negative. I mean, last time we had everybody be positive, but it'd be the same. If everybody's negative, there's also, you've got a positive or negative definite form that's anisotropic. Okay, so that's the crucial thing. If you're in this situation, which generalize what I just did, then the corresponding orthogonal group looks like, well, in this case, alpha naught's positive, everybody else is negative, so this is SO1n. And then the integer points, but the integers, you have to take all the algebraic integers in this entire field. If you take the integer points of G, then that will be an arithmetic group, and in fact, it'll be co-compact. And the co-compactness is by exactly the same proof as I used last time. Okay, there's definitely, I mean, there are definitely no solutions to, there's no solutions to have the form, yeah, this quadratic form has no isotropic vectors in that field by the same proof I gave last time. Just by applying, just applying Galois automorphism to it. Is there a question or not?
Yeah. Why do you need for all Galois automorphism? Why not just one? I mean, in the proof that you had before, you just took a suitable one that made everything positive, and then...
Absolutely. So this is one right. I got this one right. Thank you for pointing out. That's a good point. That's very good. Excellent. In fact, I said here, in order to get the thing to be co-compact, I could say just there exists instead of for all. You're absolutely entirely right. The problem is that if you have just that there exists and some of the other ones give you positive signs, then it won't be an arithmetic subgroup of G. It'll be an arithmetic subgroup of G cross some other things. Every time you have an automorphism with, if you've got alternating signs, then in fact you get another factor of your G. It'll be G cross some other stuff. And we'll see that later. That's very good. Yeah. So the co-compactness only requires one automorphism. Well, actually, it's always going to be an arithmetic subgroup, but it'll be an arithmetic subgroup not of G, but of something else. That's the trouble. And the way to say it, remember, is that every time you have every gamma automorphism is going to give you another orthogonal group. We have another quadratic form. It gives you an orthogonal group. But the point is, if that group is compact, I ignore it. We'll see that later. Compact groups don't matter. So it's okay if for every automorphism that gives you a compact orthogonal group, I just ignore it. But if it gives a non-compact orthogonal group, I mean, you can't just go around ignoring non-compact spaces. Compact space, you can sort of just hold and talk away and don't worry about it. But something huge and non-compact, that's too big to just ignore. So I have to include it as an extra factor. I'll say that more precisely later, but that's exactly right. Okay, so you're absolutely right. It'll always be co-compact if you're having a single gamma automorphism, but if you want to get a hyperbolic manifold, as opposed to some other locally symmetric manifold, then you need to make sure that all of the quadratic forms are anisotropic, are compact. Is that okay? Yeah, so no, you're absolutely right. We'll get a co-compact arithmetic group, but I thought this audience wanted to see hyperbolic manifolds, and for that you have to make them all compact. But that's the thing I haven't told you yet about why it's an arithmetic subgroup of that group. But that we'll do later. And in fact, I think maybe it's time. Oh, it's almost time to do that. Except the trouble is, before I prove that this is an arithmetic subgroup of G, I have to define what an arithmetic subgroup is. I've been putting that off for days, but I finally have to tell you what an arithmetic subgroup actually is. What did I do here? Oh no, sorry. Before I do that, there's more. Okay, so the thing is that this is a way to construct co-compact lattices in G. It's a way to construct compact arithmetic compact hyperbolic manifolds. So I think that's good. It's good that we can get some examples of hyperbolic compact manifolds this way. But it's even better than that. As I said before, if you're assuming that n is even, then this construction doesn't just provide examples of compact hyperbolic manifolds. It actually constructs all of the compact manifolds, at least the arithmetic ones. Okay, so this construction, which I think is very simple and natural, except that you have to allow number fields instead of just z, but just using quadratic forms, diagonal quadratic forms like this, putting various coefficients in it, will give you all of the arithmetic hyperbolic manifolds that are compact. Okay, well, unfortunately that's only if n is even. When n is odd, this only gives half of them. Besides using orthogonal groups like this with real coefficients there, we have to take orthogonal groups of a quadratic form with some quaternion algebra as coefficients. So everybody knows about the real quaternions. Well, also, over a number field like this, you can make quaternion algebras, and it turns out you have to look at not just quadratic forms with coefficients. You don't have to look at, it's not just quadratic forms with coefficients in the field. You have to look at quadratic forms with coefficients in some quaternion algebra. And I'm not going to get into this. It's not all that difficult, but I want to talk about other things. Okay, but if you want to get all of the compact hyperbolic manifolds, well, it's easy in even dimensions. In odd dimensions, it's fairly easy, but you have to spend a day first learning about quaternion algebras, then you can make them all. Except there's one problem. For n equals 7, besides these two, which I consider quite easy, there's something that everybody agrees is difficult. There's an extra case of what's called triality manifolds that I'm not going to try at all to explain what's happening there. Unless, I guess I can say. The point is that group theorists describe different groups, SO1n, SO2n, and stuff like that, by drawing something called the Dinkin diagram. Well, the Dinkin diagram for SO17 looks like this. It's called type D4. And the trouble is just that this is the only example of a Dinkin diagram that has a symmetry of order 3. You can rotate this. It's got a rotational symmetry of order 3, and that means that we need to take not just quaternion algebras, but actually the quaternion algebras come from the fact that this has a symmetry of order 2. Okay, because there's a symmetry of order 2, in fact, in general, for every one of these, whenever n is odd, there'll be a symmetry of order 2, and so you have to use quaternion algebras. Because there's a symmetry of order 3, you have to do something more complicated, and I don't understand it. I guess that's not saying much, but people who understand arithmetic groups really well understand this triality. But it's definitely quaternion algebras are not a big deal. Everybody's seen quaternions before, but these triality things are just something different. Okay, so if you actually want to get all the hyperbolic manifolds of dimension 7, you have to work. It's not just spending an hour learning or a day learning about quaternion algebras. You spend a couple of months learning about triality. Right, but anyhow, ignoring 7, it's easy to construct all of the compact hyperbolic manifolds that are arithmetic. They just come from quadratic forms. And the only catch is that some of the quadratic forms might have to have non-commutative coefficients. Right? But that's, yeah. Okay. So now I'm ready to tell you what an arithmetic group actually is. I've been talking about them all week. It's time to actually tell you what it is that I've been talking about. So first of all, let me remind you what an arithmetic group has been all along. It's not that difficult. To say that gamma is an arithmetic subgroup of G just means that gamma is the integer points of G. And the thing is, though, when I first gave this definition, I think I said an arithmetic subgroup is the integer points of some suitable group G. So the thing I have to do is explain what suitable means. That's actually, unfortunately, that's only the first thing I have to do. The first thing is, let me finally tell you what suitable is. But to do that, I need a definition. Okay, and I'm always assuming G is semi-simple and connected. Okay, you can talk about arithmetic subgroups of solvable groups, but that's a different story. For hyperbolic geometry and related topics, all we need is semi-simple groups. And then the good thing is that since we're in the semi-simple case, it's true that G is always Zariski closed. So if you're in algebraic geometry, you know what I mean by that. G is just, what I mean is G is a set of matrices. It's Zariski closed, except there's this problem. Technically, I have to say almost. Let me not worry about that. That just means that G might not be Zariski closed, but it's within finite index of a group that's Zariski closed. So let me not worry about finite groups here, but let me just pretend that G itself is Zariski closed when I'm saying this stuff. And all that means is that G is defined by polynomial functions on the space of all matrices. That's what it means to be Zariski closed. And so, as an example, let's look at SL2R. Okay, now SL2R, it's a bunch of 2 by 2 matrices. It's the 2 by 2 matrices of determinant 1. And the determinant function, well, it's cross-multiplying A11, A22 minus A12, A21. And this function is obviously a polynomial. It's a polynomial in these 4 variables. So what that tells us is that SL2R is, well, I knew this, SL2R is Zariski closed just by this theorem, but this actually explicitly shows that SL2R is Zariski closed. And that's the point. Any semi-simple group that's connected, any semi-simple group, connected semi-simple group of matrices will be Zariski closed. It's not obvious, but you'll always be able to find some polynomials that define that group. Okay, and so let's do another, okay, yeah. But I need to go one step farther. I need to make another definition. I need to explain what it means for a group to be defined over the rational numbers, and it just means that G is defined by polynomial functions. Well, except every G is defined by polynomial functions. That's what I just told you. The crucial thing is, though, that those polynomial functions will have real coefficients. To say it's defined over Q means that you can choose polynomial functions with rational coefficients. So to say a group is defined over a particular field means that the polynomials that define it have coefficients in that field. And so, for example, SLNR is defined over Q because it's the matrices of determinant 1, and if you write the determinants as a polynomial, just all the coefficients are 1s and minus 1s. You just multiply some things together and subtract some. You add and subtract them. So the coefficients are definitely real. If you look at SO1n, if you write down the polynomials that define SO1n, so SO1n means you take A times some matrix times A transpose is the identity. All the coefficients, again, they're just integers. In fact, I think they're probably 1s and minus 1s again. Okay, yeah, so again, it's obvious that that's defined over Q. On the other hand, if you do what I've been doing recently, put the square root of 2 into your definitions. Let's take a quadratic form with some square root of 2's in it. I think I looked this, except I'm only using 3 variables because I didn't want to have to write so much. But yeah, just put some alphas in. Then this definitely, the corresponding orthogonal group is definitely not defined over Q. Because when you write down what this means, to be an SOQ, I mean, if you got a matrix A, you take A times something with alphas in it, times A transpose should be this thing with alphas in it. When you multiply that out, you get some alphas in your equations. So there'll be polynomial equations, but the coefficients will have alphas in them. They're not rational numbers. Instead, G is defined over an extension of Q. Okay, that's what it's about. So the point is that suitable just means, now I can tell you what suitable is. Whoops. Okay, so suitable just means defined over Q. So what I've been talking about all week, I could have said this start maybe, the idea of an arithmetic group, and the trouble is I have to say a little bit more, but at least to get started, the main thing about an arithmetic group is that the integer points of G is an arithmetic subgroup of G if G is suitable and G is defined over Q. And the point is just, if you have an arbitrary, if you have a G that's suitable, a G that's defined over Q, if you conjugate it by some terrible irrational matrix, it'll now be moved to some irrational slant. It might not intersect the integer points at all. Right? So if you take a bad G that's completely irrational, it might not have any integer points. So GZ would be trivial. That's not going to be a lattice. It's not going to be interesting. It's not called an arithmetic group. But if G is sitting nicely with respect to, sort of you think of like has a basis of rational vectors, then it will be, it has a chance of hitting integer points, and in fact it will. The integer points will be a lattice, and that's what an arithmetic group is. So I think this is a quite reasonable condition. You have to put something in, because yeah, it's like if you take a line of irrational slope that doesn't have any integer points on it, but if you got a line of rational slope, which means defined over Q, then it is going to have lots of integer points. So it's exactly the condition you need. It's the non-algebraic, sorry, the non-linear version of just this fact that a line of irrational slope isn't going to have integer points. Right, so that's what an arithmetic group is. But let me actually, since it's the last day and I'm finally going to do some technicalities, and you don't have to, if you don't follow it, it's okay. But yeah, let me give you the actual technical complete definition of an arithmetic group. And this, I just need to jazz this up a little bit. The point is that that's the right idea, but the actual definition is a little bit more complicated because it's more general. We want to ignore, as I mentioned earlier, we want to ignore compact groups, and also I want to ignore just this thing I have said earlier, I want to ignore finite groups. So if two groups, if gamma 1 and gamma 2 just differ by a finite group, if gamma 1's finite index in gamma 2, or gamma 2's finite index in gamma 1, or something like that, if one of them's arithmetic, then we'll call the other one arithmetic. Because up to a finite group it is arithmetic, and I don't want to keep track of all the finite groups that are involved. And that is it. So the definition of an arithmetic group is exactly that all of these things are arithmetic groups, and anything that differs by just a compact factor or by a finite index, by a finite group, will also be an arithmetic group. And so let me write that down. Okay, so if you understand that, that's the definition. The definition is gamma is arithmetic if either it is the integer points of the group defined over Q, or it's not exactly that, but it's off by a compact factor or by a finite group. And so, all right, well, let me state what I mean by that. Let me state this. So the point is, suppose G is defined over, the point is it's not just G, maybe we add a compact group to G. So suppose G cross some compact group is a bunch of matrices and it's defined over Q. Okay, I want to define an arithmetic subgroup of G, but it turns out that G itself might not be defined over Q, so when you add on something compact, it becomes defined over Q. Right? That could happen. In that situation, the integer points of that, well, yeah, we'll just take the integer points of that. This is definitely an arithmetic group. It's the integer points of a group defined over Q. It's the integer points, so this is an arithmetic group. But now what I'm going to do is just take, this is a subgroup of G mod K. Let's just mod out K. There's an obvious projection to G. So I've got this arithmetic group. If I just project it into G, I'll still call that an arithmetic group because all I did was got rid of some compact group. Okay, so I'll still call this arithmetic. And then the last thing is that also anything that's just finite index from that will also be arithmetic. So any subgroup of G that's commensurable with gamma prime. So this is arithmetic because it differs by a compact group from something that's obviously arithmetic. Well, commensurable means just differs by a finite group. So if you look at the part of gamma that's in common with gamma prime, the intersection has finite index in gamma and finite index in gamma prime. So up to finite groups, both of these are the same group. They're both just gamma intersect gamma prime. Okay, so in that case, if gamma is just a finite group away from being gamma prime, I'll call it arithmetic. That's the construction of arithmetic groups. So the thing to remember, if you didn't get all that, the thing to remember is just the integer points are arithmetic, but I'm allowed to mod out a compact group, and I'm not worried about finite groups. Finite groups I ignore. So I ignore compact groups and finite groups. And that is actually the definition. That's what an arithmetic group is. And with that definition, I can prove that that group we were talking about is an arithmetic subgroup of SO1N. But before I do that, this probably, I've been talking about arithmetic groups all week. I finally get the definition. Is there a question about this, or is it okay? This is what I've been talking about. But I just ignored the compact factors and the finite index. Those are details that I didn't want to get into until the end here. Okay. Yeah. Okay, so now that we know what an arithmetic group is, we're going to prove, well, remember what I was supposed to prove. We had alpha as a square root of 2. We defined this quadratic form with some alphas in it. G was the orthogonal group of this form. It's definitely, there's one positive sign, the rest minus signs. So this is an SO1N. I claimed that if you took the integer points, you got a co-compact arithmetic subgroup. Well, co-compactness I've already done. It's the arithmeticity that I haven't done. So I want to show that this thing is an arithmetic subgroup. And the point is, this is the first time all week we've known what I was talking about when I said this. Okay, we now know what it means. I'm supposed to show that there's a G cross K, and the integer points, you mod out the K, and then you get within commensurable to the gamma. That's what I'm supposed to prove. Right? But the idea is that gamma should just be the integer points of G, but it's not. It's Z adjoint alpha points of G. That's why it's not obvious here. So I have to actually turn gamma into integer points of something. And the thing is, well, okay, but the thing is, that's a little bit complicated, and I'm certainly not going to do the details of that. I'll give the idea, but let me do something a little simpler. Instead of showing that this group is arithmetic in that G, let me take a similar thing. Instead of taking the integer points of an orthogonal group, let's take the integer points of something much easier. SL2R is easier than SL1S. Let's start with something easy. I take integer points, but funny integer points of an easier group, and I'll show that that is an arithmetic subgroup, not of, I mean, you might guess it's an arithmetic subgroup of SL2R, but that's not right. This is not discrete in SL2R. You have to take SL2R cross SL2R. You get an extra factor. Okay, so let me explain, though, that this SL2R, and I guess when I say it's an arithmetic subgroup, I put an isomorphism sign this because it's not even obvious that it is a subgroup. So I'll show you how to take this group, embed it in there to be an arithmetic group. That's what I'm going to do. That's the main thing. If you understand that, then you definitely understand the idea of why this is an arithmetic subgroup of G, but the details here are a little more complicated. So let's just do this one, because this I can explain fairly completely in just, well, I don't know, 10 minutes or so. Okay, so let's see why. Okay, so I'm trying to show, well, I'm just repeating what I just said. So gamma is the integer points of SL2R, but it's algebraic integer points where alpha is the square root of 2. G then will be SL2R cross SL2R. I'm going to try to show that I'm going to embed gamma in G cross G, and the crucial thing is I have to use a Galois automorphism, like I did before. So I take that same Galois automorphism of Q adjoint square root of 2. So sigma of alpha is minus alpha, but sigma of 1 is 1. Okay? And from that, I'm going to define a map delta. Delta is a map from gamma into SL2 cross SL2. And delta, so what happens is an element gamma, I need an ordered pair. The first entry, I need an element of SL2R. Well, there's an obvious element of SL2R. Gamma is an element of SL2R. So the first entry is obvious. Gamma maps to gamma, but now I need another element of SL2R. If I just went to gamma and gamma, that wouldn't be interesting. I need to do something better. Well, it turns out I'll just use gamma sigma. I'll twist the second entry. Okay, so this Galois automorphism takes any gamma and gives me another gamma. Gives me a different kind of a thing. Okay, so that's it. That's my embedding. In the first factor it's normal, the second factor it's funny, and then the point is that this embedding of gamma is an arithmetic subgroup of G. That's what I want to prove. So we embed sort of, I call it delta because I call this the diagonal embedding, but it's not actually diagonal, it's like a twisted diagonal embedding. Some of the factors get twisted. Okay. And I'm not going to do all the details, but this is fairly complete. There will be some calculations to check, I guess, maybe what I'd say. Okay, so the first thing to do is just look at what happens when we apply delta. Well, Z adjoint alpha, everybody here is something plus something times alpha. So the basis for that, a basis over Z, is just 1 and alpha. Let's apply delta to the basis elements of Z adjoint alpha. And, well, 1 delta, you're supposed to take 1 and 1 sigma, but sigma fixes 1. So 1 delta is just the point 1, 1, but alpha sigma is minus alpha. So I get 1, 1 and alpha minus alpha. These are 2 elements of R2. They're 2 vectors in R2. And the crucial thing here is that they're obviously linearly independent. Right? These are linearly independent, so they're a basis. This is a basis of R2. And you can take any basis to any other basis by a linear transformation. So there's some linear transformation on R2 that maps this basis to just the standard basis. And so that if you take all integer combinations of these vectors, they'll get mapped to all integer combinations of the standard basis vectors, which is just Z2. So there's a linear transformation that maps this ring to Z2 inside of R2. Okay, and now I'm just going to take, I've got this 2 by 2 matrix. Let me make a 4 by 4 matrix just by taking 2 copies of T. That's what I mean by direct sum. A T up in the top corner and a T in the bottom corner. So now I've got 2 copies of T together. That's something, that's a 4 by 4 matrix. And the key thing to notice is that if you apply this T hat to Z, to, I don't know, this Z adjoint alpha, 2 copies. But Z adjoint, I mean, yeah, I want this acts on R4, so I need something in R4. Well, this is Z, this is, I don't know how I'm saying something stupid. Anyhow, so I guess what is, each copy of T acts on 1, so they have both copies of T act, right? So I've got 2 copies, that's what I want to say. I've got 2 copies of this thing, that's what that says. I've got 2 copies of Z adjoint alpha, and T hat has, so I have a T act on each one. Well, on each one of those, it moves it to Z2. That's what I was supposed to say. So each one of these guys gets moved to Z2, so the 2 of them get moved to Z2 squared, which is Z4, the standard lattice inside of R4. That's that thing. So this T hat moves this funny thing to just Z4. And what that means is that if we take gamma elements of gamma, delta, and conjugate them by T hat, well, let's see what happens when you apply the matrices like that to elements of Z4. Well, this time maybe you have to, let's just walk through this. If we take Z4, well, right here, T hat moves this guy to Z4, so T hat inverse will move Z4 to this funny thing squared. So when you apply T inverse, you get the funny thing squared. But gamma delta on the something delta, that's just going to, gamma delta is going to fix this funny thing squared. So at this point, once you apply this, you still got the funny thing squared, and T hat of that will be back to Z4. So if you follow it through, these matrices all fix Z4. And what that means is you've got a matrix that preserves the integer points. It's in SLN of the integers. It's got to have integer entries. And so, well, now, my gosh, look at that. So in fact, if we just a little, I mean, I'm not going to prove this, but if you have to, you can check that this matrix, we know these matrices are a bunch of integer matrices. In fact, it's all of the integer matrices. Well, actually, that's not right. It can't be all of them, because T hat, gamma delta, T hat inverse is definitely in T hat. I mean, where is gamma hat? Yeah, gamma delta is inside of G, so it's certainly also inside of the conjugate of G, but it's all, this is the biggest it possibly could be. Definitely this group's contained its integer matrices, and it's obviously inside of this G thing, but in fact, the key thing you have to check is that it's all of the integer matrices there. I guess that's probably not obvious, but it can be checked. Okay, so this thing here is all of the integer matrices in that group, and also, it's not obvious, but once we've conjugated G this way, it's still defined over Q. In fact, I guess, yeah, G is obviously defined over Q, but it turns out when you conjugate by this particular T hat, it will stay defined over Q. That one's not obvious, but it's just a calculation to check that what you got, you can, yeah. In fact, you get something that's very obvious, has obvious rational polynomials defining it. So here, but anyhow, so this is where I'm not giving all the details, but anyhow, this thing is the integer points of something defined over Q. Well, by definition, even the easy definition, that tells us that that thing is an arithmetic subgroup. This is an arithmetic subgroup of that, but conjugation is an obvious isomorphism, so just by isomorphism, then gamma delta will be an arithmetic subgroup of G. All right? Okay, yeah, that's it. So that's how this works. The point is, I think, yeah, this is a little bit complicated, but it's definitely right. The key thing here is that once you have algebraic integers, you can do a funny, if you embed sort of this twisted diagonally, a change of basis will turn it into ordinary integers. That's the story here. Okay. And now, so this is the case we just, I think this is what we just did. Yeah, okay, so this is, oh no, this is the one I want, so what I just proved, sorry, yeah, I'm just mixed up here. So I just did the easy case. What I wanted to do, though, was this group. I wanted to take an orthogonal group and show that the integer points of that is an arithmetic subgroup. And let me just sketch that. Let me just sketch why gamma is an arithmetic subgroup of G. It's similar to what I just did, but let me just give the flavor. So if you got the flavor of what I just did, you'll get the flavor of what I'm doing here. And that's all I expect from today. This is not the kind of thing you pick up by watching somebody do once. You have to do it yourself. Sit down and look at it and do the calculations and see what happens. But the idea here is, as always, I look at that Galois homomorphism of Q adjoint alpha. So sigma of alpha is minus alpha. Well, here what happens, I think, yeah, we've seen this. I've got this group G, it's defined by this quadratic form. Well, G sigma is going to be the group defined by the sigma of this quadratic form. So it's the orthogonal group with, and I'm missing an alpha there, sorry about that. Right? All these have alphas. Oh, I've got the numbers are all wrong too, sorry. And it's not a 5, it should be n. So everything's wrong, except the fact that it's all plus signs there, okay? Anyhow, once you do sigma to it, all the things that were negative get turned positive. So that has all plus signs. So this group is SO5, or conjugate to SO5. All right, that's a crucial thing. Okay. Yeah, sorry about that, but yeah, that's, certainly I got it's all plus signs is right. And now we'll use that usual map that I used last time, the twisted diagonal embedding. That, yeah, okay. So we've got a map, just you always just take whatever you had and also the twisted thing. That gives us some group gamma delta. So what is that? It's ordered pairs, it's gammas, and there's gamma sigmas. Well, delta of an element gamma will be gamma, which is contained in G, and then when you twist by sigma, you get an element of G sigma, not an element of G. Okay, so that's the thing here, is that before I was embedding, my gamma delta was inside of SL2R cross SL2R. Well, that's just because when you do a Galois twist of SL2R, it's still where it was. But here, the G sigma is not the same as the G. And the last time I should have put a G sigma also, but conjugating SL2R by a Galois automorphism doesn't move it anywhere. So gamma delta is inside this product instead of SL2R cross SL2R, but it's analogous to what we did last time. And just like last time, after a change of basis, and the main change of basis, remember that Z of alpha can be mapped to Z2, and then you just do an n-tuple mapped to n-tuple, have that matrix T hat. So this T hat will be T plus T plus T plus T m times. But anyhow, after change of basis, this gamma delta, just like last time, will be the integer points in my G cross G, or actually G cross G sigma this time. Okay? And that tells us then that gamma delta is an arithmetic subgroup of G cross G sigma. Okay, so this is just like what I did on the last slide, okay, except I've got an orthogonal group instead of SL2R, so there's a little bit of twisting in the second factor. But now here's the difference. The only thing that's different is that this G sigma is SO5, it's compact, and we can ignore compact groups. I'm allowed to mod out compact groups and just project into G. And when you project, when you mod out G sigma and project into G, well, what are you getting? You get gamma delta projected into G is just the gammas. I'm just getting gamma. So gamma is an arithmetic subgroup in G because you can mod out the compact factor. And so that's why I needed, well, okay, I guess we'll see this again. Okay, so gamma is an arithmetic subgroup of G. And this method that I've used here is called restriction of scalars. This method of this diagonal embedding that turns algebraic integers into just ordinary integers is called restriction of scalars. So let me just, I've done a couple of examples. Without a proof, let me tell you the general theory that happens here, at least for orthogonal. Yeah, in general, restriction of scalars, this method of taking Galois automorphisms and diagonal embedding and then take a basis and all that stuff, that's called restriction of scalars. In general, if you've got a group that's defined over not Q probably, but some extension of Q, and here alpha does not have to be the square root of 2. Alpha could be any algebraic integer. Okay? Then, you look, this field will have a whole bunch of, well, actually, this might not be a Galois extension. If it's a Galois extension, then I just want to take, this isn't quite right. You'll have an entire Galois group of these things. In general, instead of the Galois group, what you look at if it's not a Galois extension, you look at all the possible embeddings of your field into C. Except that there's a little technical point. I don't want to take all the embeddings. If you've got one, I mean, the complex numbers have complex conjugation. So whenever you have an embedding, you can just compose that with complex conjugation. Those two are considered equivalent. So I take one out of each pair. So I take what's called the non-conjugate embeddings. But again, that's a technical point we don't have to worry about. So the easiest thing is, if Q of alpha is a Galois extension that's contained in the real numbers, so this just, so what I can say is just under minor technical conditions, these sigmas are just all of the Galois automorphisms. So maybe that's the way to say it. Under mild technical conditions, I'm just taking all the Galois automorphisms, but in general, there's a little bit of detail to worry about. Then, if we define G star to be the product of G cross G sigma, except I have to take the product of all of the possible G sigmas, okay? And I didn't bother with a G at the start because one of these guys is going to be the identity. Okay, so this is really G across a G sigma across a G sigma, a bunch of different G sigmas. If I call that G star, that group, after a change of basis, will be defined over Q. And furthermore, if you look at the integer points of that group, you take G sigma, take the integer points of our original G, that'll be embedded by a twisted diagonal embedding in G star, so that it actually becomes the integer points of G star. So it's definitely an arithmetic subgroup. Just via the map, it's a twisted embedding map. That's restriction of scalars. If you take the integer points and embed them diagonally, they become integer points. And I guess technically, since I'm at the end, I'm actually doing things right for a change. I'm assuming here the technical condition that, in fact, Z adjoint alpha is the entire ring of integers of Q alpha. That's just a technical assumption. Don't worry about that. And I was worried there might be number theorists in the audience that would say, no, that can't be right, but yeah, this is right if you make that assumption. Okay, so that's the general theory. Let's just talk about what that means in the case of interest to hyperbolic geometers. That's G, works for a general semi-simple group G, but the groups people in this room are most likely to look at are ones defined from a quadratic form. So suppose we've got a quadratic form and its coefficients are in some algebraic number field. Then the integer points of the orthogonal group is definitely an arithmetic subgroup of, well, probably not just G, it's probably a product of G's. You have to take all these conjugates of it, okay? But all the conjugates of an orthogonal group will just be an orthogonal group with respect to a different quadratic form. And this is exactly the answer to the question I had earlier, why I needed all of the sigmas to give you positive coefficients. Well, that's because if all of these guys are compact except the first one, I can just mod them out and I'll get an arithmetic subgroup of G. But if some of these are non-compact, I'll have an arithmetic subgroup of a G cross a G, instead of being in just the G I wanted. Okay, so this explains, I hope, why earlier I required an assumption about all of the automorphs instead of just one. And it also says, so yeah, even if I have just one, well, yeah, it doesn't. That was just to get co-compactness. No matter what's true about the Galois group, you're going to get an arithmetic subgroup. It's just maybe not going to be in the group you want. It's going to be it's the group you want cross a bunch of other stuff. But if you can make all the other stuff compact, you can ignore it and you get an arithmetic subgroup for the group you're interested in. So I would like to definitely thank you all for your for your perseverance and also for coming to all these talks. Thanks a lot.